this is AQA A-level chemistry, yeah, all equations patterned, yeah. There's bare equations here that the teachers don't tell you about. You get me? And just bare like small things in it. So I'm gonna go through all of that, yeah. At the start it's gonna be year 12. I put like a little year 12 thing, yeah, so you know, yeah. And the rest of it is gonna be year 13, yeah. So everyone will benefit from this. Trust me, if your grades are dead right now, yeah, if you pattern this and you learn all these equations, yeah, they will increase by like at least 10 marks. Trust me. There's bare random questions in the paper, yeah, that people don't tell you about, and they just come and they say state this equation, state that equation, yeah. So this is basically all of them covered, yeah. Just get into it then, yeah. So first things first, yeah. Thermal cracking, yeah. Thermal cracking occurs at 1000 degrees Celsius, yeah, or 1200 Kelvin, and 70 atm of pressure, yeah, or 7000 kilopascal, yeah. Catalytic cracking makes aromatic compounds, yeah, and occurs at 450 degrees Celsius, yeah, or 720 Kelvin. It uses zeolite catalyst and just above normal pressure, yeah. Alright, calm. Complete combustion, so always when you combust like an alkali like this, yeah, what will happen is organic compound, yeah, is it's gonna combine with oxygen and it's gonna create CO2 and H2O, yeah. These two are always the products, so you just write these two and you write oxygen and then you balance after using the carbons and hydrogens of whatever you're combusting, yeah. And then incomplete combustion, yeah. As you see, it's gonna be something similar to this. As you see, instead of carbon dioxide being made now, and now you're making carbon monoxide, and because of that ratio of deleting the two there, what's gonna happen now is you see how I've got 3O2. If I divided all these man by 2, yeah, I would have CH4 1.5 O2. So do you see how there's 1.5 O2? That 1.5 means that's insufficient. Yeah, so we've got insufficient oxygen, yeah, which is the reason why CO is being made here, yeah? Calm. So for every one molecule of CO, 1.5 O2 is made, whereas for every CO2, 2 O2 is made. Alright, calm. Carbon monoxide is a toxic gas here and has no odor or color, yeah? Oxides of nitrogen are also harmful, yeah? Catalytic converters remove these products. This uses a rhodium catalyst to convert the products into CO2 and H2O, yeah? So that's a catalytic converter that's going to use a rhodium catalyst. Calm. Sulfur impurities can lead to acidification of water as they can react with rain to form a weak H2SO4, yeah? Flue gas desulfurization can remove these impurities. Calcium oxide and gypsum are used here. So here you got calcium oxide plus 2H2O plus SO2 gives you CaSO3 plus 2H2O, yeah? Memorize this equation, yeah? This is the equation for flue gas desulfurization, yeah? Ozone depletion, calm. So it is a simple reaction here. Ozone, O3, is going to react with a Cl free radical. Cl is going to rip off one O, so that's going to become OCl, free radical. Obviously, O2 can bond by itself, so that's why it doesn't have the free radical on it. So that's O2 now. And then OCl is going to react with the initial, which is O3 in this sense, yeah, like when you do free radical substitution and whatnot. And that's going to combine with the O3 to create 2O2 plus Cl free radical. As you see, the free radical is a kind of a catalyst here, yeah. It's at the start Cl and at the end Cl. It didn't get used up. And the overall equation for this is 2O3 to 3O2. So as you see, ozone is being converted into oxygen, yeah. So that's the situation here. As a result, that leads to ozone depletion, yeah. Alright, called magnesium and water, yeah. So magnesium reacts with water, Mg plus 2H2O to get MgOH2 plus H2. However, with steam, yeah, it's faster and it provides the reaction with extra energy, yeah. Magnesium burns with a bright flame to form magnesium oxide, a white powder, yeah. So they'll ask you, yeah, what's the equation for magnesium with steam instead of water? So this is the one. Mg plus H2O gives you MgO plus H2, yeah. And they'll ask you what's some observations, yeah. So you'll say that has a bright flame. You'll say that it forms a white powder, that kind of thing. Solubility of hydroxides, yeah. So the solubility of group 2 hydroxides increases down the group. So hence magnesium hydroxide is the least soluble and barium hydroxide is the most soluble, yeah. Allow that there. You get me? Solubility of sulfates, the solubility of group 2 sulfates decrease down the group, hence the magnesium sulfate is the most soluble and barium sulfate is the least soluble, yeah. Again, in the you know what I'm saying? Computer's bugging out. Alright, calm. Test for sulfate ions, yeah. Barium chloride is used as a test for sulfate ions, yeah. Sulfate ions, yeah. As it is reacts to form barium sulfate, which is a white precipitate, yeah. So Ba2 plus any sulfate ions, yeah, will produce BaSO4, and that's going to be bait. That is a white precipitate, which shows that it's therefore it was sulfate ions, yeah. Calm. Metal extraction. This is a big one, yeah. They come and they're like, yo, what's the equation for metal extraction, yeah, of titanium and magnesium, yeah. So TiCl4 plus 2Mg gives you MgCl2 plus Ti. There's a simple displacement reaction, not much going on here, yeah. Calm. Okay, now we're getting into some proper, yeah, equations where it's all going to be repetitive, yeah. So essentially here, yeah, reactions of halide ions with H2SO4, yeah. So this is for F and Cl. NaF will react with H2SO4 to make NaHSO4 and HF. NaCl will react with H2SO4 to make NaHSO4 plus HCl, yeah? So as you see, it's a similar basis here. We're reacting with these two, we're getting the same thing, the only difference is the end ion is different, HF for F and HCl for Cl, yeah? Bromide ions, it can happen in two different cases. We can have a situation like NaBr, what happens NaBr plus H2SO4 makes NaHSO4 plus HBr, similar to the last two, so it's easier to remember those three. And then the fourth additional one, yeah, 2HBr plus H2SO4, Br2, SO2, and 2H2O, yeah, easy. Iodide ions, yeah, so iodide, we've got three different ones here. We've got NaI plus H2SO4 gives you NaHSO4 plus Hi, that's similar to the previous three. Then we've got this one, which is similar to the bromine one. And then it goes further on, yeah, 6Hi plus SO2 makes H2S, 3I2, and 2H2O, yeah? So memorize all these equations as well, yeah? Alright, test for halide ions, yeah? So if I've got Cl minus, and I want to test for that, I'm going to add silver nitrate, yeah? And what is going to be produced is a silver chloride, white precipitate, yeah? And then it's gonna that proves that it was chlorine, yeah. If a white precipitate gets made, if a cream precipitate gets made, it proves it was Br minus, yeah. And if a yellow precipitate gets made, it's I minus. Normally chlorine bleaches white, yeah. Br is normally like cream, yeah, and then iodide is normally yellow, yeah. And then you can also further add dilute NH3, yeah, which basically with Cl the precipitate will dissolve. With Br there will be no change in this precipitate, and then with the AgI no change, yeah. And if you add concentrated, precipitate dissolves, no change, yeah? Chlorine reaction with cold water. So here you've got Cl2 plus CH2O, gives you chlorate plus Cl minus plus 2H plus, yeah? So that's a reaction with cold water, yeah? Chlorine decomposition of water in UV light. So during UV light, chlorine will decompose water. And so that will basically break up into 4HCl plus O2. Bleach production, yeah? So this uses a cold aqueous sodium hydroxide plus Cl2, and that basically produces sodium hypochlorite, which is a key ingredient in bleach production. Yeah, so we'll ask you what's the equation for bleach production or something along that line, and this is the equation right here. Yeah? Hydroxide tests, they turn a red litmus paper blue or turn universal indicator blue purple. Yeah, it's because they are our main component of alkali substances. Yeah, cool. Carbonate test, yeah. When mixed with an acid, the substance with the carbon ions will fizz, yeah, and as a result, CO2 will be released, and then they can be collected and bubbled through lime water, which will turn cloudy when in contact with CO2, yeah. Flame tests. So flame tests: calcium brick red, strontium red, and then barium pale green, yeah. Ammonium test. If there are ammonium ions, ammonia gas will be given off naturally. This is a base, and hence it will turn red litmus paper blue. This is done over a petri dish, yeah? You can also use NaOH to produce the ammonia gas faster if you want, yeah? PVC, polychloroethene, yeah, has waterproof properties, yeah? It gains these properties when plasticizers are added. Fermentation. So fermentation, yeah, it goes from C6H12O6 to 2C2H6O plus 2CO2, yeah? And essentially what's going on here is this is going to be done using yeast and under 40 degrees, yeah, that's the conditions for fermentation, yeah, as well as the equation. Yeah, calm. So essentially glucose, ethanol, and carbon dioxide, yeah. Alright, calm. So potassium dichromate, yeah. So potassium dichromate is basically oxidizing agent, yeah, and it can oxidize certain things here to basically show what they can turn into. So when it does this here, primary alcohols, they turn green, from orange to green, yeah? The potassium dichromate. Secondary turns from orange to green as well. But tertiary doesn't change because it can't be oxidized, yeah? So therefore, you can tell the difference between primary, secondary, and tertiary. For primary and secondary, you have to do further tests, yeah? But you can basically eliminate tertiary. Now, failing solution, yeah? Failing solution goes from blue to brick red if an aldehyde is present, yeah? Hence, we know if an aldehyde is present, so if the primary alcohol got oxidized, it's going to turn from blue to brick red. So that's how we know we can differentiate between primary and secondary. Also, tollins here. If an aldehyde is present with and then a silver mirror will form, yeah? If not, then it will remain colorless. So same as failings, but this time a silver mirror will form. That's actually silver as well. And yeah, that's basically tollins. Alkenes test, yeah? Bromine water will go from orange brown to colorless if a double bond is present, yeah? So if an alkene has double bond something, it will go to colorless, yeah? Calm. Now this is year 13, basically, from this point, yeah? So production of the NO2 plus ion, yeah? So for nitrobenzene, The electrophile used is NO2 plus, and is basically used in this. This is produced from these two equations. So you need to memorize these two equations to produce the NO2 plus electrophile, yeah, and that will be used in this situation here, electrophilic substitution, yeah, where the NO2 will substitute with the H, yeah. This is a known equation. I'm not going to go through this mechanisms in this video, yeah, but you just need to know the equation to actually produce that NO2 plus ion, yeah. So these two equations here. Friedel-Crafts acylation, yeah? So for Friedel-Crafts acylation to occur, a reactive intermediate must first be produced from the acyl chloride and an aluminium chloride catalyst, yeah? So Friedel-Crafts acylation is basically used to introduce an acyl group, so the RCO, yeah, onto an aromatic ring, yeah? But we need that RCO, we need that intermediate group, yeah? Hence we're going to use acyl chloride and an aluminium chloride catalyst, yeah? And this is the equation for Friedel-Crafts that you need to state, yeah? And so you state this one and that produces the RCO, yeah? This is the actual reaction that will happen with Friedel-Crafts alkylation reaction, acylation reaction. This is basically what's going to happen here. Alright, calm. But you don't need to know that equation. Obviously, you need to know the mechanism later on in a different video or something. But the actual equation to produce that intermediate is previously, yeah? Alright, calm. Reduction of nitriles. Yeah, so reducing nitriles through hydrogenation can produce amines. This needs a reducing agent or a combination of hydrogen and nickel. Also needs LiAlH4, so reducing agent, right? Nitrile going to amine, so write this equation down as well. You need to know the equation for this. So essentially, hydrogenation is basically adding the H. So yeah, reduction, bro. Pattern. Production of aromatic amines, yes. So aromatic amines can be produced by the reduction of nitrobenzene using concentrated hydrochloric acid and a tin catalyst, yeah. So you use tin and hydrochloric acid, and you go from NO2 nitrobenzene, yeah, into an amino aromatic compound, yeah. Calm. Cationic surfactants, yeah. So these are good complexes with a positive and negative end, yeah, which makes them good conditioners. And the two ends are attracted to different substances, yeah. Hence, they prevent static from building up on surfaces, yeah. The head of the cationic surfactant is positive, yeah. Hair typically carries a negative charge due to the presence of amino acids like cysteine with ionizable groups, yeah. So cationic surfaces can easily adsorb onto the hair surface, yes. They can attach onto the hair surface, yeah. Not absorb, not go into it, but adsorb, yeah. Calm. When cationic surfaces adsorb onto the hair surface, yeah, they form a thin, positively charged film. This film helps to reduce friction between individual hair strands, making the hair feel smoother and easier to comb. So that's like the conditioner effect of it, yeah. Cationic surfactants have the ability to attract and hold on to moisture as well. So they retain moisture that can help hydrate the hair and appear like it's wet. Yeah, the formation of a thin, positively charged film on the hair surface by cationic surfactants can also enhance the hair's natural shine as well. Yeah, so that's why it's, certain man with the slick, you know what I'm saying, with the conditioner, yeah? Alright, calm. Period 3 metals, yeah? So we got Na plus 2H2O, it gives you NaOH plus H2. Easy, man, easy, yeah? Mg plus 2H2O gives you MgOH2 plus H2. Easy, man. Yeah, so if you can remember what they create, you should be able to balance it, or you can just straight up memorize the equation. Period 3 oxides, yeah? So it's important to memorize all the oxides and what they actually look like, because some of them you might not know. So sodium oxide, easy, yeah? Magnesium oxide, easy. Aluminium oxide, maybe you don't know it's like that, but you can work that out easily, right? By doing you know what I'm saying, two aluminiums need to balance three oxygens, right? Silicon dioxide, phosphorus oxide, some people may not know, yeah? So it's P4O10, yeah? Sulfur dioxide, SO2, sulfur trioxide, SO3, yeah? Oxides with water, yeah? So with these equations, you just need to memorize all of these, bro, yeah? So Na2, so that plus that gives that, that plus that gives that, that plus that gives that, that plus that gives that. Easy, man. Just memorize this, pause the video, memorize it. Yeah, there's no other way around this. You can find your own ways, your own things to memorize. That's how it is, bro. You just need to memorize it. Acid-base reactions produce salt and water. Again, we've got acid-base reactions here. It's going to produce some form of a salt and water. You need to memorize what these salts are, memorize the numbers. You can work this out slightly, but it's very hard. Just like to do it in practical, you know what I'm saying, situations. So just memorize these equations, yeah, recall them, go do something, come back 30 minutes, just recall these. Trust me, it's worth it. Aluminium oxide, yeah. Aluminium oxide is partially ionic and covalent, hence it's insoluble in water. Hence it can act as both an acid and a base. This is known as being amphoteric, yeah. So it can act as an acid, or it can act in terms of a base, yeah. So here you got two equations showing that. So Al2O3 plus 3H2SO4 produces Al2SO4 3 plus 3H2O, yeah. So as you see in that situation, it acted as a base, yeah, and it neutralized the SO4. H2SO4, yeah? Whereas here it's acting as an acid and it's neutralizing the NaOH, yeah? And that, I'm not neutralizing, but you see what I'm saying, yeah? Hydrated metal ions on NaOH, yeah? So obviously here, the color that that the equation is here is basically the color of the compound produced, yeah? So just needs to just memorize these, man, honestly. The black means colorless, yeah? So white basically, no color. And yeah, you just need to memorize these, man. So Fe H2O 6 2 plus that gives you that color, and just keeps going, man. Yeah, this equations will have some kind of similarities with them, as you see 2 plus produces 2, 2 plus is 2, and these are very similar equations. 3 plus, there. But just memorize them and it'll become easy. Amphoteric salts, yeah. So since aluminium salt can act as an acid or a base here, it's amphoteric, yeah. And so when sodium hydroxide is added in excess, the salt can also act as an acid and it's hydrolyzed further, yeah. So this is the first equation. So this is when it's added to the NaOH here. AlH2O6 3 plus that gives you AlH2O3 OH3, yeah, plus 3H2O, and that's a white precipitate, yeah. Then when it's in excess, when you have sodium hydroxide in excess here, so as you saw before, 3OH excess, 4OH here, then it's going to hydrolyze further and it's going to create AlH2O2 OH4 minus, yeah, and this is colorless, yeah, plus 4H2O, yeah. Calm. Hydrated metal ions with NH3, yeah? So basically, again, memorize these. You just need to memorize this format. Yeah, what they produce, what color. Calm. When ammonia is added in excess, so when ammonia is added in excess, yeah? So if you look at the previous one, these are with NH3, but when it's in excess, yeah, the copper, yes, the one in the middle, it will actually turn into a darker blue. Yeah, so before it was like that, now it's a darker blue it's gonna produce, yeah? Hydrated metal ions with Na2CO3. So again, just these two equations. Memorize. Memorize these as well. So this was CO3. So you can categorize them as I categorize them, right? So you can say with NH3, this one's with CO3, and you just keep going. Hydrated ions with Cl minus. So again, you can keep going here. Okay, calm. This is the ion color of each oxidation state of compounds with V, vanadium, yeah? So VO2 plus would be yellow. VO2 plus with the 2 on top, like ion, would be blue. V3 plus is green. V2 plus is violet, yeah? Production of vanadium oxide, reduction of vanadium oxide into vanadium oxide. That's 5 to 4. Yeah, that's going to be 2VO2 plus 2E minus plus 4H plus goes into those two, yeah? Equation for Tollens reagents. So we talked about Tollens earlier, Tollens reaction. So it's going to be going into Tollens reagent, how to actually produce it, what actually happens. So RCOH plus 2 AgNH3 2 plus 3 OH, that basically reduces or whatever, and it will turn into Ag. Yeah, so just solid silver, and that's why you have the silver mirror, yeah? Redox titrations, yeah? So redox titrations are a little bit complicated, a little bit, yeah? I'll make a video on it as well. But essentially, yeah, these three equations you need to memorize, yeah? And then once you can memorize this, you can basically use it to solve redox titrations, yeah? So memorize these three equations, and then you'll basically see that there's a formula here, yeah? So MnO4 minus to C2O4 2 minus, these are the ratios, yeah? I advise that you learn the equations or the ratios, which is basically of electrons, so 5 of MnO4, right, compared to the 1 of Fe compared to the 2 of E3, yeah? So what I advise here is that you memorize these all these equations, yeah, and you also memorize the ratio, yeah, so it becomes easier when you go to redox titrations, yeah. Not redox titration, yeah, redox titrations, yeah. So yeah, so memorize this ratio, memorize the equations, yeah. Contact process, this is the equation for the contact process. Overall, that's the contact process. 2SO2 plus O2 using V2O5 catalyst gives you 2SO3, yeah. And then obviously the actual like reactions in between is V2O5 plus SO2 gives you V2O4 plus SO3. V2O4 plus half O2 gives you V2O5, yeah. So that's the contact process. That's what happens in the contact process here. And it will ask you to just state the equation for the contact process. Ligand substitution reactions. So here again, we got the color scheme going on here. So CuH2O6 2 plus 4Cl gives you yellow, CuCl4 2 minus plus 6H2O. Yeah, these are going to be ligand substitution reactions for the hydrated metals. Okay, here again. Here again. Calm. So those are the three ligand substitution reactions. And also here, terylene is a polyester, whereas Kevlar and nylon 66 are polyamides. Yeah? And that's the end, yeah. Now, this video, I didn't really go in depth and explain every single equation, yeah, because there isn't really a point, yeah. If you know chemistry behind it, it's minor. You understand? The whole point in these is to be able to recall them and memorize them, yeah. So the whole point in this video, yeah, is for you to basically just see all the equations, have them all together on one page, yeah, so you can memorize everything, yeah. And then when it comes to tests, it's easy. I know it seems like a lot, yeah, but deeper. That's over the whole chemistry course. I'm pretty sure that's pretty much every equation you need to know in the whole chemistry course, yeah. So if you memorize all of those, you're good, mate. You're solid, yeah. If you do all of those plus the reaction mechanisms, bro, it's a different level, man. You know what I'm saying? Yeah. Trust me, it will increase your ability a lot, yeah. So yeah, that's it.